Hello, in this video we are uh, continuing with the two body central force problem, and we will be looking at the differential equation for an orbit. Now, as discussed earlier in the previous video, what we had obtained is the total energy equation, and we had obtained the first integrals, and those were the equations which were associated with any object which is under the influence of the central force motion, and those were the equations that were concerned with it. The central force equation of motion for the central force that was thus obtained was mr double dot, which is equal to j squared divided by mr cube plus fr, giving us the force, the form of the force which is dependent on the position vector. Remember, fr, well, f, that is the force that was there, was equal to fr r cap, and fr, if you remember, is of the form of del u by del r taken negative, where u is the potential energy of the system that is being discussed. And with that, well, if we consider the r dot is simply dr by dt. We can also write it as dr over d theta and d theta by dt. Now remember, this is differential equation for that orbit that we are about to discuss. This was the equation. Now we'll be discussing the differential form of it, and this is dr. Now d theta by dt, as you know, will end up as theta dot. That was our notation, shorthand notation that we had been using. And well, this is dr by d theta, of course. And dr, so what was the value of theta dot that we had obtained in the previous video? That is equal to j divided by mr squared, and that is exactly what we are going to substitute over here. So what we are going to get is, for r dot, we'll be having the value as d by dr by d theta times of j divided by mr squared. Now further taking the double derivative of it, what we can obtain is d by dt of this term over here. This term can come up front. This is a constant term, and what remains there is dr by d theta, and that will equate to, well, I can just do a few adjustments over here. I can bring down that d theta over to this side, and because I have a d theta at the denominator, keep the bracketed term as such, and of course there will be dt to end it with, but because I have introduced d theta over here, I'll be taking the d theta over there as well, so that these d thetas, they can cancel out, and all you had is d by dt, which was in the first place over here. Now this is j by mr squared in the bracket. The bracketed term remains as such. I prefer not repeating it, but just in case. So this is equal to d by dt, and well, this is again theta dot, isn't it? And this being theta dot, we can just use the value of j by mr square over there. So what we get is d by d theta, j by mr squared, dr by d theta, and again we have j by mr squared over here. Now let's do a bit of substitution if we can. We substitute a variable u for 1 by r, such that when you have du by d theta, what you get is minus 1 by r squared dr by d theta. Now if we have that value over there, well, looking at this part of the this part of the equation, it looks familiar, doesn't it? So what we do is we just use those values, we substitute that value over there. What we do is the above term for our double dot that we have obtained, that is this one, this changes to uh, this j by mr square that is over there, that can come up to the left hand side, j divided by m. Well, it's there, but instead of the r square, remember 1 by r is u now, so instead of that r square in the denominator, we have u square in the numerator. And to top it with, we have the minus sign coming up from the uh, inside with this du by d theta. Now remember, this will be 1 by r square, 1 by r square. I'm just marking it for you, 1 by r square dr by d theta. Only thing that is missing over there is the minus sign. Well, we can bring the minus sign out, and what we have is j by m that is left, and that j by m can come outside, so j square by m square now, and d by d theta of du by d theta. I hope that's clear to you. And now this is j square u square divided by m square, double derivative of d square u by d theta square, double derivative form. And well, we take it back to this equation. This r double dot is to be substituted over here. So instead of r double dot, we have minus j square u square divided by m square. One of the m that is over there multiplied, that gets cancelled out, so we are left with only the m in the denominator. This is d square u by d theta squared, and the terms on the right hand side, well, j square, remember 1 by r is u now, so this is u cube, and the m stays at the denominator, plus obviously f of r. Instead of f of r, what I can do is I can just use f of 1 by u, because r is equal to 1 by u. And well, I bring this thing to the j square terms to take them as common. I take the minus as the common term, j square is common, u square is common, m is common, and so what lies in the bracket is d square u divided by d theta squared, and also I have a u left out from this term over here that was going on to the other side, and on the other side of the equation we have f of 1 by u. I can just take the minus sign from here and put it over to the right hand side. This looks pretty okay to me. This is what the equation, the differential equation for an orbit looks like. Now, considering the inverse square law that we have studied so far in cases of gravitation as well as in cases of electrostatics, those laws are inverse square laws. So what we have is the form of, this is for the inverse square laws. For the inverse square laws, what we have is f of r takes the form of k by r square. K is just a constant term over here. The important thing is that it depends inversely on the square of the distance or the position vector between the two objects, if we are considering two body central forces. And obviously it is for the attractive cases in case of gravitation, and likewise they are in minus form, in negative form. And as we know, for central forces, this is of the form of negative of del u by del r. So what we get over here is, by integrating, we know that u is equal to minus of k divided by r, which is quite known to us because We know the form of the gravitational potential as potential energy, as well as the electrostatic potential energy in case of attractive forces involved. So this value of u tends to 0 as r tends to infinity. That means at greater distances, this is the nature of these kind of forces that are involved. The potential here drops to 0. It vanishes completely for greater distances. So this is how we are representing the forces in terms of the central forces, in terms of the position, uh, where we are involving we are looking at the inverse square laws that we have studied so far in gravitation, in electrostatics, and likewise. Now, as we have dealt with the Kepler's law of planetary motion, which is obviously a part of gravitation, and I had also obtained the uh, constant form of the aerial velocity in the previous on the previous video, previous occasion in the previous video, while obtaining the equation uh, for the motion of the uh, object under central force. So in that case, we can just get a lead to the deduction of the Kepler's law, and in order to do that, we will be proceeding as follows. So let me take a fresh page for you, because we will be doing a new derivation uh, for that. Okay, so in order to consider the Kepler's law, or again we are dealing with gravity, that means it is the inverse square law that will be involved over there. The force which was dependent on r, because r is now 1 by u, I can take f of 1 by u is equal to, now remember it was k by r square, but 1 by r is taken as u, so I can just take it as k u square. In case you have forgotten, you can take a look at the previous few seconds or minutes, or I will just write it over here, since u is equal to 1 by r, so f of r is now f of 1 by u. Now d square u, that is the equation that we have obtained, d square u by d theta squared plus u, and on the other side, if you take the j square u square divided by m, well, that taken to the other side, what you have is m divided by j squared u squared. It's as easy as that. And that when multiplied with minus k u squared. Now this term can be taken to the other side. Well, there's a u square over here, there's a u square over here, they can surely cancel out. And then this term taken to the other side, well, you have from the differential equation, you have this d square u by d theta squared u, and this becomes plus of mk divided by j squared. And if I am to take, now this is equal to 0, of course, if I am to take this as x, then this surely will be d square x by d theta squared, and d square x by d theta squared plus x, that is taken for this entire term, that equates to 0, and what that gives me is a solution of the form where x is equal to, now if you can observe this thing, this is simply an oscillatory case. In fact, the 0 is included. So in this case, you have this in the form of harmonics, that is a cos theta. Let us say there's a constant term theta dash. This is the solution to this above differential form. And with that solution, because we know that x, instead of x, what we have used is we have used this term for x, so u plus mk divided by j squared on the left hand side, that is equal to a cos theta minus theta dash. We can bring back the r term now. So with that u going back to that 1 by r form, what we have is this can go to the other side. Well, there is a small error over here because I have used the minus ku square. Actually, there's no minus sign over there, so this goes to minus. It hardly makes a difference with the differentiation, and this term, however, is minus over here. So what we have is 1 by r minus mk. Remember, just in the previous page, if you remember, what I had obtained is in the previous page what I had obtained over here is minus of f of u, f of 1 by u, that is this over here. This is minus of f of 1 by u in the previous page. So taking that into account, this will be in positive value. So that minus that I have indicated over there, that won't be there. So this is 1 by r, and mk divided by j squared is equal to a cos of theta minus theta dash. And to present it in a decent way, what we can do is we can multiply this entire term by this j square by mk whole divided by r for the first term. In the next term, this will be minus 1, and on the right hand side we have j squared divided by mk, and you have an a cos of theta minus theta dash. Well, the 1 can just go to the other side. J squared divided by mk whole divided by r. I'll tell you why it's in that form, because it'll be a meaningful expression in that case. J square a divided by mk cos theta minus theta dash. Well, if we are considering this, then this one over here at the top, we'll be writing it as L divided by R, and this will be equal to 1 plus E cos theta minus theta dash. And this is going to help us in the Kepler's formulas that we have. Well, how do we use it? We will be discussing that in a separate video, but as for the central force cases, we'll be continuing with our derivations that will be involving some of these terms for sure. Well, what are the substitutions that I have used over here? L is for j squared divided by mk, and E is here equal to j square a divided by mk. Well, E just has an a extra in it, but also what you can obtain by the equations that we have discussed above is that E is equal to 1 plus 2e j squared divided by mk squared. This also comes handy. Well, this is all under root. In case you are unable to follow this one, you can just write that down to me, and I'll help you with another video for that in case. But well, it won't be a problem. I hope you can derive it all by yourself. It's quite easy considering the equations that we have dealt with. You can just substitutions will help. Now this is an orbit's eccentricity. That is why it is represented, it's quite apt to represent that term with E, this one and this one for sure. And that is why this kind of an expression will be handy in the deduction of the Kepler's laws, and with the starting from the first, the second and the third law. The second law partially we have derived it for the first and the third laws. You can use this kind of a deduction um, and obtain the desired result. These kind of expressions, they look horrible though, but these kind of expressions are going to give you evidence about the uh, fact that we are studying, and they will be useful to determine the values, the unknown values, as well as the complete analysis of the orbiting motion of the planets around, about the sun, or even the electron about the nucleus. So these equations are of much importance than they look at present. This equation that we studied, this however represents the general equation. This is the general equation of a conic section. Conic section with one focus. This is the general equation of conic section with one focus, and with focus at the origin, of course, and with eccentricity E, and the value or the magnitude of eccentricity decides the nature of the orbit. I'll be writing it over here for giving it to you in the same page, so that you don't have to, so that I don't have to turn to the other page every time. So this E, when that is greater than 1, the value of the total energy, that will also be greater than 0, and then the conic that it will be describing, that will be a hyperbola. The conic that it will be describing is a hyperbola. This is the first condition. And for E equating to 1, E will be equal to 0. As you can see over there, E is equal to 1, so square of that, those terms cancel out, and so you have E is equal to 0, and that is for a parabola. And then for E less than 1, the eccentricity is less than 1, the total energy is obviously going to be less than 1, and that is when you have an ellipse, which is the case of the planetary motion. And then for E equals to 0, well, here also, as you can see that, sorry, E is not less than 1, E is less than 0. So E here being negative term that you can see over there, that is the potential energy term is dominating, and we are experiencing the attractive force. Now for E is equal to 0, you have the value of E to be a negative, but a fixed value over there, that is mk squared divided by 2j squared, and that is for a complete circular path. So these are the cases that are associated with this kind of eccentricity and the general equation of a conic section. That is having a focus at the origin, of course. In the upcoming video, we'll be discussing about the various properties, closure, and stability of the orbits that are determined by the energy, the potential energy term, and many more things which have numerical evidences, and then we'll be proceeding further into the topic as well. Till then, thank you for watching.